All right, this is the second video on sequences. So I want to start by looking at the three statements on the screen. The first one is read, the limit as n approaches infinity of an equals L. The second one is an converges to L, and the third one is an converges to L. All of these three mean exactly the same thing. A textbook will go through a formal definition of this, but we will talk about this as the definition being as n gets higher and higher, so as n approaches infinity, the terms in the sequence an get arbitrarily close to the limit L. So in other words, they get closer and closer to whatever L is, or we can think of it as them getting infinitely close to whatever L is. To do that, we look at sequences a lot like we did functions, but we're always talking about the limit as n approaches infinity. And so there are a few things that we're going to accept as fact based on what you study in first semester calculus course. Okay, so a few informal things we should remember from Calc 1. One, and again, what we're writing very informal. So one thing is if we have a number over infinity. Okay, so if you have a finite number over infinity, then that goes to zero. So if you have any number divided by something that's getting infinitely large, that approaches zero. Also true if it's negative infinity. If you have infinity divided by a finite number, but that number is not zero, then that goes to infinity or negative infinity, depending on how the signs work out. So if you have like a negative divided by a negative, that goes to positive. If you have positive divided by negative, that goes to negative. And so again, definitely informal, but a way to think about what we're talking about. If it's infinity divided by zero, that's less clear. So those are two things that we want to definitely be aware of. If we have exponential functions, so like if I'm talking about 3 to the n, or say 1/4 to the n, as n goes to infinity, anything in the form b to the n, that approaches infinity if the base b is bigger than 1. That approaches 0 if the base b is between 0 and 1. So we want to accept those things as fact. You can think quickly about the graphs of those to realize why. So if I'm talking about 3 to the x, then the graph looks about like that. If I'm talking about 1/4 to the x, the graph looks about like that. It approaches 0. And so if we have f of x equals 1/4 to the x. Again, nothing I'm writing here is very formal, but this is a good way to think about things that when we're dealing with sequence limits. So we're going to look at a bunch of different problems where we try to find the limits of a sequence. But the first thing I want to look at is I want to look at this calculation. So let's say you have 32,000 plus 0.00029 minus 0.000000002. Okay, and that divided by 0.00000000001 plus 2 minus 1 over 457 something huge with a bunch of zeros after it. Okay, so without using a calculator, I want you to think through what that would be, and don't get an exact answer, but think through basically what is that expression equal to. Okay, so pause the video and think about it for a second and then check it with me in just a minute, but don't spend more than maybe 20 seconds on this. Okay, so 32,000 is basically the top. The bottom is basically 2. And so this is basically 16,000. The decimals that I've got on there are so ridiculously small that the top is incredibly close to 32,000. The bottom, the 0.0001, that is so very, very small. 1 divided by 457 with so many zeros after it, that's incredibly small. So this is basically 16,000. So when we do sequence limits, we want to think about what's called dominance of terms. We want to think, okay, which one is getting the largest as n goes to infinity? And in most cases, we can clearly see that one term is so much bigger than the others that the others don't matter as n approaches infinity. In fact, the comparison is going to be more ridiculous than 32,000 plus point whatever, however many zeros to 9, and minus point however many zeros into 2. So we're going to do a bunch of problems that say show whether the sequence converges or diverges. And we're not going to do formal proofs, but we're going to give an explanation as to why the limit is what it is. And so we're going to say show whether the sequence converges or diverges, and if it converges, find its limit. Okay, and so the first problem I want to look at is if I have a sub n equals 5n squared plus 6n over 8n squared minus 176. Okay, so when we look at that problem, the way I want us to deal with it is I want us to look at it and say, okay, we've got 5n squared plus 6n over 8n squared minus 176. If you look at the two expressions on the top, the two terms on top, they're both power functions, meaning they're both n to a power. It's n to the second and n to the first. On the bottom, they're both power functions as well. It's n to the second and n to the 0. When you're comparing power functions, it's easy to determine which one is larger. So as n goes to infinity, 5n squared is so much bigger than 6n that 6n does not affect the limit as n goes to infinity. Same thing in the denominator, 8n squared is so much larger than 176 that 176 doesn't affect this. If n is 100 billion and then you square it and then times 8, 176 is so much smaller than 8n squared that it doesn't really affect what's going on. It's more of a ridiculous comparison of like than it is between like point a bunch of zeros and a 2. Okay. So then the limit of the first expression approaches the limit of the second expression. I'm using an arrow, meaning that I'm talking about the limit as n goes to infinity. Notice we're not saying equals, so those two expressions are not equal to each other. This is equal to the next one, but it also approaches 5/8 because the n squareds cancel. So this is one way to show that the sequence converges or diverges. In this case, we're showing that it converges to 5/8. In Calc 1, you may have learned other ways to do that, and you're welcome to show them in that way. Another way to write the notation would be, and we'll do this in red, we can write the limit as n goes to infinity of 5n squared plus 6n over 8n squared minus 176. We're going to say, okay, that's equal then to the limit as n goes to infinity of 5n squared over 8n squared, which then is equal to 5/8. Either method is okay. We don't need to do both, but we'll accept either method in our class. Okay, so let's look at a second problem. So again, the directions are going to remain the same. So the directions for the rest of the problems in this video will be show whether the sequence converges or diverges. If it converges, find its limit. So okay, so problem 2 is going to be an equals 6n minus 356,241 over 5n to the third plus 857n. So what I'd like you to do is pause the video and do this problem like we did the last problem, and then check it with me in a few minutes. Okay, so when we look at this, the top has both power functions, and so we'll accept as fact that 6n is infinitely larger than 356,000, even though 356,241 seems large. And we're talking about, we could have that number with 100 million zeros after it, and then we're multiplying by 6. So n is approaching infinity. It's so much bigger than the other one that, again, the comparison is more ridiculous than the comparisons of the decimals we were talking about before this. So the top approaches 6n as n approaches infinity. The bottom approaches 5n cubed. And 857n does get very large, but nowhere near as large as 5n cubed gets. Okay, when we simplify that, that then approaches 6 over 5n squared. And now we've got a constant number over 5n squared, but 5n squared approaches infinity. So if we have a constant over infinity, the sequence goes to 0. So we know that from Calculus 1. We could also use limit notation here. We could also show some more algebra to more concretely prove this, but we're just trying to show the basic idea of how to get the limit of the sequence here. Okay, so let's do one more like this. So if I have a sub n equals, say, 5n squared plus n cubed minus 147,360 n over, say, 8n squared plus 35n minus 16. So see if you can pause this video, try the problem, and check it with me in a few minutes. Okay, so when we look at this problem, we take the entire expression, so 5n squared plus n to the third minus 147,360 n over 8n squared plus 35n minus 16. If we look at the numerator, n to the third kind of dominates the other two terms. So as n approaches infinity, n to the third is so much bigger than the other two terms. The other two terms don't affect the limit as n goes to infinity. Same thing in the denominator. When we have 8n squared, that is so much larger because we're squaring n. So if n is a number where we have 1 with 100 billion zeros after it, when we square that, that's very, very much larger than 35 times that number. So we get to here. That simplifies to n over 8. As n goes to infinity, obviously the top goes to infinity, and then we divide by 8. That still goes to infinity, which means that this sequence diverges. So the answer to this problem would be diverges if we're trying to show whether it converges or diverges. On the first two problems, when we say approaches 5/8 or approaches 0, we're saying that the sequence converges to 0. And so if you wanted to write a word to describe that, you could. You could describe it as converging to 0, but the arrows imply that. Okay, let's look at some examples with exponential functions in them. So number 4 is going to be an equals 4/5 to the n. And so a few minutes ago when we were talking about informal idea behind limits, we said that, okay, bn approaches infinity if b is bigger than 1, bn approaches 0 if b is between 0 and 1. So if we go down here, 4/5 to the n, we'll take without further proof that 4/5 to the n approaches 0 because it's an exponential where the base is between 0 and 1. So 4/5 is obviously bigger than 0, it's smaller than 1, and so we'll say, okay, as n goes to infinity, we understand that approaches 0. So then if I have this, if I have an equals 7 over 6 to the n, then we'll accept as fact that that approaches infinity. So 7 over 6 to the n approaches infinity, so then this sequence, diverges. Okay, so let's look at a more complicated example. So if I have the sequence an equals 3 to the 2n minus 1 over 5 to the n plus 6. Okay, so here we only have one term on top, one term on bottom, but we're going to do some algebra that's a little bit different. So normally you'll see me, and that's what we're going to do here. I'm going to write this as 3 to the negative 1 over 5 to the 6th times 9/5 to the n. And I want to show the algebra on the side, but what we're doing there is we're using properties of exponents just in a little bit weird way compared to maybe the way you used it in algebra. So we can split subtraction or into two separate exponents. So I can make it 3 to the 2n times 3 to the negative 1, because when you multiply two things with the same base, you add powers. I can split this into 5 to the n times 5 to the 6th. So that's where I'm getting this expression. So I've got 3 to the negative 1 over 5 to the 6th times 3 to the 2n, but I'm thinking of it as 3 to the 2 to the n over 5 to the n, and that's how I'm getting this. So you've got 9 to the n over 5 to the n, which is the same thing as 9/5 to the n. Well, because 9/5 is bigger than 1, that part approaches infinity. The first part is positive, so this is positive here. So we have a positive number times positive infinity, which means this goes to positive infinity. That means the sequence then diverges. Okay, let's look at another example. So if I have an equals 3 to the 2n plus 5 minus 10 to the n plus 6 plus 9 to the 2n minus 1 over 3 to the 4n plus 1 plus 6 to the 2n minus 5 plus 2 to the 5n plus 7. Okay, so when you have exponentials, meaning you have a number to the n, we're going to be able to say that one of those is dominant based on whichever has the largest base. But looking at the algebra from above, 3 to the 2n minus 1 really ends up becoming 9 to the n. And then 5 to the n plus 6 really ends up becoming 5 to the n. So when we're looking at this problem on number 7, 3 to the 2n plus 5, we're thinking, so we're going to put this in purple, we're thinking of that as 9 to the n, because we're going to be able to factor out a coefficient like this and get 3 to the 2n like that. This one, it's going to be 10 to the n, because we're going to have 10 to the 6th times 10 to the n. And this is going to be 81 to the n, because we're going to have 9 to the negative 1 times 9 squared to the n. So we take this term when we're looking at the dominant term. On the denominator, we've got 81 to the n here because it's 3 to the 4th. We've got 36 to the n here because it's 2 squared. I'm sorry, 6 squared. And we've got 32 to the n here because it's 2 to the 5th. So the largest is 81 to the n. Again, we could show algebraically, it would be more complicated to show which of those are bigger, but if we think of it this way, it's clear that 81 to the n gets much, much larger than 9 to the n or 10 to the n as n goes to infinity. So when we write out our work, we're going to write, okay, 3 to the 2n plus 5 minus 10 to the n plus 6 plus 9 to the 2n minus 1 over 3 to the 4n plus 1 plus 6 to the 2n minus 5 plus 2 to the 5n plus 7. The largest term on top is 9 to the 2n minus 1. The largest term on bottom is 3 to the 4n plus 1. Using the algebra we were talking about a few minutes ago, we can rewrite this as 9 to the negative 1 over 3 to the first times 81 over 81 to the n. And what we're doing there is we're rewriting 9 to the 2n minus 1 as 9 to the negative 1 times 9 squared to the n, and 3 to the 4n plus 1 we're rewriting as 3 to the first times 3 to the fourth to the n. Okay, 81 over 81 is 1. The number 1 to the n approaches 1. We learn in Calc 1 that 1 to the n is an indeterminate form. That's true when the base is approaching 1 and not actually 1. Here the base is actually 1. And so the 81 to the n's cancel out. And this approaches 1 over 9 to the first times 3, just because we move the negative exponent down to the bottom. That means this approaches 1 over 27. All right, and so this is our informal proof that that sequence converges to 1 over 27. As you can see, this one gets a little bit more complicated, and it definitely requires a good bit of practice. I want to look at one more example, but then you need to do some problems before advancing to the next video. So the last problem I want to look at is if I'm looking at a sub n equals 3n to the fifth plus the square root of 8n to the 12th minus 6n plus 1 over 3n squared plus the cube root of 5n to the fourth minus 8n plus 17. Okay, so if we're looking at this problem, as n approaches infinity, the largest term on top, we've got n to the fifth outside of the fraction, or outside of the radical, but the biggest term inside is 8n to the 12th, and we're taking the square root of that. So the variable part of that will end up being n to the sixth, because the square root of n to the 12th is n to the sixth. We divide the power by 2. So when we're looking at the dominant term, we're looking at power functions here. So n to a power, the n to the sixth will dominate. So the square root of 8n to the 12th is what we're going to take out of that. Here we've got n squared versus n to the 4/3. 2 is bigger than 4/3, so this is the term we take as the dominant term. So we've got an equals 3n to the fifth plus the square root of 8n to the 12th minus 6n plus 1 over 3n squared plus the cube root of 5n to the fourth minus 8n plus 17. That approaches the square root of 8n to the 12th, because that's the biggest term on top, over 3n squared, because that's the biggest term on bottom. We can simplify that by rewriting this as n to the sixth times the square root of 8 over 3n squared. That approaches n to the fourth times the square root of 8 over 3. That then approaches infinity. So this sequence diverges. Okay, so when we're doing these problems, it's going to be acceptable to do this and take the dominant term when we're talking about all similar function types, meaning all power functions in this problem, where they're all n to a power, n to the fifth, square root of n to the 12th, square root of n, and square root of n to the 0, and then on the bottom, n to the second, cube root of n to the fourth, cube root of n, and then cube root of n to the 0. We'll accept the dominant term when it's the same type of function. Same thing on this problem. These are all exponential functions, like 9 to the n, 10 to the n, and 81 to the n, and then 81 to the n, 36 to the n, and 32 to the n. When it's all similar types of functions, then we take the dominant term and deal with the problems this way. When we start to mix functions, we look at other methods to do these proofs, these sequence limits, and so we'll talk about that in a later video. At this point, you should look at the handout called Sequences 1. You'll be provided solutions to that handout, and you should do the first 20 problems. You should be 100% comfortable with the first 20 problems before moving to the next video. So if you do have questions, please let me know. Thanks for watching.